I should probably explain the title, because the liberal art of science has all the right buzzwords, because I was giving the title before I knew what I would be talking about. And I think the temptation is in such topic and this conference to talk about the two cultures, the relation between humanities and sciences. But what I decided to do is to try to offer a voice from within science, to not get into this whole discussion about what's more important, what's the use of each, but just what are the problems of science education and the public understanding of science that comes through education. And to start, I think it's always good to define the terms. When we talk about liberal education in the context of science, obviously, I think one of the nice definitions is the knowledge for its own sake. That's we're not learning a job. It's not qualification. It's an education. But when it comes to science, I think Michael Matthews put it in a very good way that it's not only in the liberal tradition. Science education should not only be about the science, it should be also about science. It's not only the content of a particular science subject, it's actually the understanding of what science is. But the problem is that then obviously we have the question of what is science? And Reverend Michael Heller from Krakow, in a recent interview, proposed a quite good classification, which I think it will be, I won't be using it very explicitly, but I think it's good to keep it in mind. That when people speak about science, they might mean people. And people, it's not only Newton, Einstein, Copernicus, but also the institutions. That science is what's going on at universities, at the research institutes. But that's limited, and I think the history of the strong program of sociology of science, the Edinburgh School, Latour and all those things, proven that it's wrong. Science, the content of science, transcends the people, transcends the institutions. On the other level, and I think that's the most popular level of thinking about science, are the results. And I think we need to separate facts, theories, and the technological spin-offs when we talk about results of science. And obviously, philosophers of science will say that there are no such things as naked facts. That every fact is dependent on theory, and I totally agree. But there's a difference between saying that we're talking about the law of gravity and then saying that things fall down. The fact that it is a fact that things fall down. The theory of gravitation only gives interpretation, gives meaning, gives explanation to that simple fact that we observe. And in my talk, I will devote quite a lot of time to the technological spin-offs, because I think there's a huge confusion when it comes to science. That a lot of people think of science purely as the technological applications of science, which I think is mistaken. But most scientists, if you talk to a scientist, they will talk about the method. Science is not the results. The results are changing. The method is also changing, but how we define ourselves as scientists as opposed to any other scholar is the method by which we approach the problems and the questions that we ask. So, being an astronomer, I will use mostly astronomy as an example of how those notions propagate. So, let's start from the question, why do we even bother? Why astronomy in particular is important? And this is a quite profound question, and the International Astronomical Union recently published a report on why is astronomy important, how to justify the pursuit of astronomy. And in the conclusions, the author is right, although we have focused mainly on the technology and knowledge transfer, perhaps the most important contribution is still the fact that astronomy makes us aware of how we fit into the vast universe. And that's, I think most people would think that that's important in astronomy. But when they started writing the report, they say pursuing this question is a fundamental part of being human, yet in today's world it has become increasingly important to be able to justify the pursuit of the answers. Studying the universe is not enough to do astronomy. And the examples of why astronomy is important that they were giving was mostly applications of techniques developed in scientific research. It was mostly computer code actually. Someone wrote and then it was applied in a different discipline. In industry, aerospace sector, spy satellites were an actual example, which is beautiful because it's so wrong. Spy satellites are 20 years ahead of any telescope that we have. It's actually the military that gives us, when they find a new, better way of spying on Earth, they give us the technology to actually produce a new telescope. The energy sector, that was mostly code that was written. And medicine, which is actually, that's true, that I think that's a very important application because the problems that we are solving are often involved in imaging and of very noisy data. That is very applicable in medicine. But I think it's important that these are not strictly astronomical problems. These were technical obstacles that we stumbled upon when we were trying to study the universe. And we solved them because, well, they were technological problems. And engineers would do the same job. You don't need an astronomy question to develop a new technique. Any engineer is capable of doing that. In fact, scientists often are quite bad at solving those and it takes a lot more time. Often when we realize the problem, the answer comes. It's just that we stumbled upon the problems first. But, so why is astronomy important? Personally, I think because of that. This image is a tiny, tiny patch of the sky. Yet every single object that we see, every dot, is a galaxy. There's not a single star in this image. And these are only the bright galaxies that we've managed to register using the Hubble Space Telescope. There's a lot more to be seen in this image if we actually stare at it for a longer time. The universe is a big and complex place. And we live in it, on a tiny planet. That's the reason why we're doing astronomy. The wonder when we stare at the sky. I think it's harder to appreciate this because of light pollution. Up to the 19th century, up to the Industrial Revolution, every single person lived with the beautiful starry night. So we don't see it in the cities. Immanuel Kant was writing about the moral law and the starry sky above him. It was just a reality in which they lived, the wonder of the skies. And we lost it, and then we need to invent reasons to actually do it. So I think the big danger for science education in the word tradition is confusing science and technology. Because that will influence the way we think about science and the way we teach science. And skipping through different areas in which the danger. Oh, sorry. I think start from the fact that the main difference is in the sort of questions that we ask. And it's important to remember that it's not the way that science is more noble than technology, than engineering. They're just asking different questions. Engineering is amazing. In fact, engineering is what makes our lives better, easier. And you must remember that ancient civilizations, or civilization across the globe, had amazing technology. But they weren't necessarily scientific. So, for example, Egyptians and Babylonians especially, had amazing astronomy, but was seen only as a tool for predicting the movements, for astrology. The cosmology of those civilizations was still mythical. It wasn't scientific cosmology. And only when pre-Socratics come along, they started asking the question, well, can we explain it as a machine, as a natural cause? A machine is probably a bad word, but what are the natural causes for what we observe? Not just, well, I will tell that Jupiter will be in that and that place on the sky in 2 weeks. And I think Whitehead is quite right when he said that although there were people of scientific inclination across the globe, we find those people in China and other civilizations, it's a very Western thing that we suddenly invented science, and science propagated within the educated society. And then we can argue why it was the Greeks, and then obviously Christianity has a strong influence. But also, what Whitehead points out is that it's probably the most universal part of the Western tradition. It's sometimes hard to explain some pieces of art to someone coming from a different civilization. Yet today, scientists are working in a global community and they communicate very easily. Science is the best, well, not the best, but it's an amazing expert product of Western culture. That I can work with people across the globe, and then we understand each other easily. There is no cultural misunderstanding. There might be a misunderstanding when we're trying to go for drinks afterwards at the conference, but not when we're doing science. So going into the dangers of confusing technology of science, Matthew Crawford wrote the very nice article on actually liberal education in science, but he made a survey of science textbook for American high schools. And what he discovered was that not only they weren't actually explaining science, they were just a collection of facts, a lot of frames saying, well, this and that. But also, they were justifying studying physics as exactly that. Oh, do you have an iPad? That's physics. CDs, that's physics. No, physics is the Newton's law of motion. There's great wonder in understanding the complexity of reality around it, the way it works. And often it's not just focused on technological applications, but that's an increasing problem in Britain. It's the well-being. Science, biology is justified as, well, dietary advice, how to be healthy. It's if you have chemistry, geography or physics, oh, it's global warming, source of energy. Like that's great, but that's not why we do science in the first place. And Frank Furedi, in his book Wasted, Why Education Isn't Educating, he used it in different contexts, but I think the title he gave to one of the chapters, The Unhappy Shift to Happiness, where education is seen as, well, trying to justify the application. It's better, your life will be better, purely because we have those applications. That's not why we're doing science. In academia, I'm being slightly, I think we shouldn't overstate the dangers. We are still doing science. Without all the problems, administrative problems, we still succeed in progressing with knowledge. But I think the big problem is producing PhDs. Being a scientist is seen as a set of skills that you can be taught, and then you're supposed to produce science. The publish or perish culture. You can ask if it's actually producing knowledge or just information. You can collect some data, do the analysis, publish a plot. But is it pushing our knowledge? Sometimes we need more time to actually think about what it all means. And Lee Smolin, in his quite controversial book, The Trouble with Physics, contrasted the culture of particle physicists, of shut up and calculate, that they believe that sorting out details will bring deeper understanding. He contrasted it with gravity physics, so Einstein, that tradition, in which actually the philosophical considerations, the reflection on what it all means, was more important. And he's quite scared that the fact that shut up and calculate dominates, the next great revolution in physics might come from outside. It might not be an academic at all, not a professional scientist. But even Richard Feynman, the famous Nobel Prize winner, who was, I think, a symbol of the shut up and calculate culture, he wasn't, if not negative, he was at least indifferent towards philosophy of science, any metaphysics, reflection on what we were doing. In his memoirs, he still emphasized that he never accepted a job that didn't include teaching. For him, just doing research was a dangerous job, because research cannot be hurried. Creativity cannot be hurried. A scholar is mainly a teacher, and the research should happen on the way. The understanding comes from teaching, not from just sitting and trying to produce another result, although that comes as a byproduct. And I think in the wider context of society, it's by focusing on applications, we often apply theories and sciences prematurely. I think, well, psychology is a good example. How many therapies are now being withdrawn after damaging a lot of people? And when we think about the pre-war period, in which how much evil came from assuming that we know how it works. I mean, I'm talking explicitly about eugenics, and things like that, when they believe that obviously intelligence as you're born with a certain intelligence, so we should just test it and separate people. It's like some people shouldn't have children because they will be stupid. And now we see it as horrible, but then it was science. It was validating everything. And also when we see that the application, and it's not the question how it works, but more like how we can do it. That often shifts the moral questions from should we do it to can we do it. There's availability of certain methods or medical methods. So I mean we can argue if that's true or not, and I think bioethics is one of the fields in which there's a lot of controversy. And Zygmunt Bauman, a sociologist from Leeds, called it the modern promise of comfort. The fact that I can solve a problem, I can do this and that, means that, oh, well, comfort dominates. We shouldn't care if it's good or bad. If it brings comfort, that's fine. We can do it. So, following from that confusion within the understanding, I would like to draw some conclusions for the actual content of science education within the liberal tradition. And at the beginning I mentioned it's not only teaching science, but it's also about science. And when it comes to teaching science, and obviously specialists in different disciplines will know it best, but I think again Frank Furedi points to two important things. Skills, which is a buzzword these days in education, transferable skills, cannot be separated from the content. We teach skills, we learn skills through applying them to a particular discipline, to a particular subject. There's no such thing as a general skill. And also, I think he basically supports the claim that we cannot focus on applications because education is about transcending our everyday experience. It's not what I experience around. It's teaching about the world, the way we discovered it, moving beyond common sense, beyond the everyday experience. That's a transfer of knowledge that should happen in schools. But turning to teaching about science, I think it's important to remember the universal scientific method, the linear model of discovery. That I go, I make an observation, I make a hypothesis, I test it, discovery happens. It's a myth. And I'm not saying that there is no such thing as a scientific method. The scientific method is a very complex thing, and it cannot be separated from people, and it cannot be separated from the institutions. Because discovery is always messy. It can be accidental. We're looking for one thing, we're finding another. It's often noticing something that is not obvious. And that's luck, that's personal talent, also experience. However, justification. So when we write a paper, then we can argue that there is something, that there are criteria of science, of justification of science. But that's a logical reconstruction of a process that already happened in a very random, in a very messy way. Going back to Matthews, he believed that because science is constantly changing, the content of scientific knowledge is constantly changing, to actually understand science, we often need to turn to philosophy and we need to turn to history of science to understand how an idea developed. But there's, I think it should be emphasized, philosophy of science is not science. A lot of discussions about science, and I think that's a lot of in the postmodernist tradition, what they were discussing were philosophical reconstruction of science that had nothing to do with practice. Because a lot of philosophy of science is about explaining the scientific method, that no one really applies. It captures elements of that, but it's not science itself. And also, I think but coming back to this, the fact that science, the content is constantly changing, it's very important to avoid anachronism. I think there's a danger, and I know that a lot of American programs in liberal arts and sciences try to include, for example, reading Ptolemy, Copernicus, and then Galileo. But an average student in medieval times wouldn't read that. These were too advanced texts. They were monographs. There is a whole tradition of textbooks explaining what goes into the Almagest and what goes into the Revolutionibus. And also because science is about the change, it's about discovering new facts and new understanding. We need to be up to date when we teach it. We can refer to science, to history of science to understand where the ideas came from. But we cannot avoid teaching the latest understanding. Because, Szepietowski said scientists have future in their bones. As much as he was saying that basically everyone else doesn't, I think that the important thing is that science is directed towards the future. We are always interested in the next big thing, and that cannot be denied. If it's the future of humanity, that's a different question. But yeah, so when I say that we should teach the latest content, the importance is because in every single epoch, the background on which the culture is formed comes from science, from the scientific understanding of the universe. And C.S. Lewis in the Discarded Image makes the statement that it's only the curious bit that propagated the farther. That's why we know about Freud, well, we know about Einstein because Einstein was a bit quirky. It's not that people actually understand his theory, all those things. And he made this claim about medieval literature. But that's, further studies show that that's not exactly the case. That people in the medieval times actually had a fairly good idea of the details of the model of the universe, the Ptolemaic model, geocentric model of the universe, including distances. So it's already, the quantity was already included. They had a vague idea of the size. And so, as an example, this is an image from Auerbach's book, so that's quite late. But this is a single celestial sphere with all the distortions in a planet moving on an epicycle. But my point is that they had an image of the spheres actually existing. The reality of the spheres was discussed. It wasn't just a mathematical model to make astrological predictions. And in fact, in Dante, I know it's possibly not the best example, but I felt that I should put Dante in a talk to an Florence. In Paradiso, by this heaven in which the cone of shadow which your world makes has its tip, she was taken up. By she, it's Venus. And your world is Earth. So what he's referring to is that you have the Earth in the middle, the sun is going around, producing a shadow. And the tip of that shadow, because we know it's a triangular, was touching the surface of Venus. It's a very precise quantitative statement about the distances in the universe as it was perceived at the time. And it seems that most of the educated audience in medieval times had this idea. So we need to remember that science is a background, even if we don't think about it this way. We always have a certain image of the universe coming from the sciences. So then the question is, what should we teach, if that's so important? And I think coming back to the specification of what science is, I think we can either teach results, the current state of knowledge in specific subjects, and then we can ask the question, which subjects? Or we can try to teach the methods. And science is a buzzword these days, science works, science everything, we can solve everything by science. But then we need to consider how to teach scientific method that is applicable to a fairly wide range of subjects. But that's actually doable, I think, because there are a few universal concepts, the concept of chance, probability, correlation, and causality, that goes across disciplines. I think that's doable. And I wanted to show some examples, and specifically from Britain, because I think the liberal tradition in the United States is well developed. In Europe, and specifically in Britain, it's not, and there are only a few examples. But they will be quite informative. So the New College of Humanities, which is also referred as the Grayling College or the Dawkins College, probably the most important competitor to Benedictus in London, they have this core course called Science Literacy. And they include cosmology, fundamental physics, that's mostly taught by Lawrence Krauss. So Lawrence Krauss is the author of the book The Universe from Nothing. And he explains how the universe just popped into existence and then admits that, well, you need space and quantum mechanics for that. So it's not exactly nothing. Then biological evolution, genetics, you can see Dawkins contributing to that, and human evolution and dispersion. And to be frank, I agree with that list. Because one is giving us the understanding of the physical world around us, on the grand scale and the very small scale. So the most fundamental level. And the second one is informing about the complexity that we see around us, of the animate rather than inanimate. The other example is the Arts and Sciences program at University College London. And they, rather than teaching specific subjects, have those core courses in Quantitative Methods and Qualitative Thinking. I think that's absolutely amazing. Because on one hand, they say, well, we need to learn statistics, you need to understand how to tackle probabilities, how to see if something is just a random behavior or it's actually significant. I think that's very important in social sciences. And so the complex. But they have, of course, in qualitative thinking, saying explicitly that not everything can be answered in terms of quantity. There are certain judgments and certain reflections we need to make in a qualitative manner about values, about meaning. And going specifically to the quantitative methods, we cannot ignore mathematics when it comes to science, but a lot of educators in mathematics admit that the problem of mathematics is that after the logical program of Russell, Whitehead, Hilbert, mathematics became artificial. It's all about abstract entities, whereas that's not how most of the mathematics used in sciences was formed. It was always created to tackle the problem at hand. And often understanding the problem from which the mathematics developed gives us a better understanding of that mathematics. And I think calculus is a good example when mechanics is developed by Newton. And it was at the same time invented by Leibniz to solve the same problems. They just realized the problems and they invented the whole mathematical formalism. And as the great Russian physicist Zeldovich said, every physicist knows what's a derivative. A derivative is the rate of change of a function. It's just that when you learn physics, you just pick up the intuitive understanding. The formalism comes later. It's what you understand in a very tacit way. And probability, which it was developed for gambling. And I think that's very practical. But in the end, it brought us the understanding of chance, the timing, or it allowed us to time the chance. And also we use it, most importantly, to know the limits of quantitative inquiry. Again, the question, I have a number, I measured a number. How well I know it? That all depends on probability theory. So, I think to conclude, what to teach. And obviously being a cosmologist, I will start from cosmology, and I don't have time to justify it, but there are reasons to teach cosmology. And I think a lot of writing by Helge Krag, a historian of science from Denmark, explains that it's, as Popper said, the most philosophical of the sciences. It's the background for all our understanding of the universe. I think we need to teach genetics and evolution, and I think it's crucial, especially in the Anglo-Saxon sphere. It's less of a problem in the continent. The conflict is not as pronounced. In the United States, and I'm not actually sure about the sources of that conflict in Britain. Some people argue that it was an import via English. But there is, you see it, you hear it so many times. Oh, I don't believe in God, I believe in evolution. Are they incompatible? Maybe they are, maybe they're not, but it's not, I think there's a lot of tension in the Anglo-Saxon sphere that's not necessarily that present in the continent. But also, we need to teach probability and statistics, because that's the general method in which a lot of sciences function. And those concepts can be taught within the framework of those two subjects. And I mentioned neuroscience because there's a big problem after Descartes and the dualism that he introduced between mind and body. And I think we still have a bit of a hangover, intellectual hangover from that. Because the same problems will be tackled differently by psychologists and psychiatrists. The psychiatrist will start from giving you pills. The psychologist will try to talk to you, and you might have the same problem. And that shows that there is a bit of a split in the way we perceive us as conscious agents, or the embodied cognition problem. But I put it in a bracket because neuroscience is still developing, and I think we still don't really have, it's not a mature subject. We can argue if it's mature or not, but I think it's not yet there to be just taught as an introductory science course. So I think I will finish on that, because these are the conclusions that I wanted to draw, and I think it's visible that there is very little application here. Those things are they're about understanding and about the wonder, not about the technological applications. Thank you.